Hello there, welcome back. This time we'll be talking about implicit differentiation, and I've got maybe a little bit of a surprise for you, at least for me. I spent quite a bit of time working on these slides, and I don't think I'll need to do a bit of writing on the screen. We'll see. Okay, implicit differentiation in your book, that's section 2.7, as you can see. We're going to do three things that makes it look a little bit simpler than it is. The first part you've actually been doing up to this point once you got into chapter 2, finding derivatives explicitly. And we'll get into what that means, and then we'll get into finding derivatives implicitly, because sometimes you can't do it explicitly. And then we'll look at a real-life situation and see how implicit differentiation can help you. So, explicit and implicit functions. Easy for you to say. Okay, so this is an example of the explicit form. One way you can tell is you've got the y on one side all by itself. 1y. Not y squared, not 7y, 1y. That makes sense. That's the way you're accustomed to seeing those. It's explicitly written as a function of x. In other words, if someone gives you an x, you throw it in here, you do a little bit of calculation, and out pops the y. Just like a function, only explicitly. Now, here's one that's not quite perfectly simple. It's sort of explicit and sort of not. Notice that on the left-hand side you've got xy instead of just y. However, you can do a little bit of a rewrite, and there's your equation, explicitly in terms of x. Y equals 1 over x, you're in business. Rewrite that so it's ready for differentiation. So you can use the power rule, differentiate it, bring that number out front, multiply it times the existing coefficient, which was a 1, reduce the exponent by 1, and then do a final rewrite or simplification. Now, that's not too bad. But in these situations, we've got something that's a little bit more complicated than that. There's no easy way to take this equation or this equation and solve it so you have y equals some expression in x. In that case, you need implicit differentiation. Bingo. Or drum roll if you had a drum. So, this is the help on the way. Implicit differentiation. The main thing to remember is that you need to keep thinking about the chain rule. The chain rule is your hero. If you want to find dy dx implicitly, you have to do a little bit of adjusting. You can't quite differentiate as usual, but the chain rule is going to be your help. So here's an example coming up that shows you how you can do that, and we've got 4 examples. First of all, we've got the 3x squared. We'll take them one at a time. Differentiate that one. In other words, you're going to differentiate the 3x squared, and you get the 6x. That's pretty simple. And the second one, you get the 6y squared, but because you're differentiating with respect to x, you take the derivative of the y, which is a function itself, and the derivative of y itself is dy dx, the dx, because it's with respect to x. Third one, take the derivative of x plus 3y. The derivative of x is real simple, just the 1. The derivative of 3y, 3y itself, you get a 3. Then you take the derivative of y because it's with respect to x. Now, what doesn't show here is that if you wanted to be a slave to the program, when you take the derivative of x, yes, you get the 1. Since you're taking it with respect to x, then you'll have dx dx. But just like any other fraction, if you have the same thing on the top and the bottom, it's equal to a 1. So 1 times 1 is 1, and you only show the 1. For part D, xy squared. A little bit more interesting, perhaps. You're going to use the product rule because you have x and you have y squared. So you take the y squared. That's the part you're going to leave alone here. You're going to take the derivative of x times that. Or I guess if I start again, the derivative of x is the 1. The derivative of y squared is the... I should start that again, shouldn't I? Okay, xy squared. We need the product rule. There's the derivative of x. Leave the y squared alone. Leave the x alone. Take the derivative of the y squared. 2y, since we're taking with respect to x, the derivative of y itself is dy dx. Just a little bit of cleanup at the end here, moving that 2 out to the front, and we write our derivative like this. So here are some guidelines, ones you just saw, but you didn't see all of them. You differentiate both sides with respect to x. Now it could be something different. We're going to start with something you're more familiar with. Write the results so that all the terms with dy dx are on the left side. And everything else that isn't a term with dy dx goes on the right side. Factor out the dy dx. If this is getting confusing, don't worry, we've got a good example coming up. Factor the dy dx out of those terms on the left. And last of all, the factor that you got in front or trailing the dy dx, the other factor, divide both sides by that, and you end up with dy dx equals some expression. So you can actually end up with something that has dy dx. What's a little bit different, though, is what's on the right-hand side after the dy dx equals might have an x and y as well. So that's a little bit different. So here's a good example for us to follow. We want to find dy dx, and there's our equation. This is an equation that has x's and y's, but there's no way you really want to take this and try to solve for y. So, you're going to differentiate both sides with respect to x. So here's your expression. And there's the -4 on the right-hand side. You're going to differentiate both sides. Split them up. Do each term individually. So you're going to take the derivative of y cubed, of y squared, of minus 5y, and also minus x squared. Now on the right-hand side, since -4 is a constant, the derivative is 0. So here we go. The derivative of y cubed, bring the 3 out front, down to y squared, because y is not x and we're differentiating with respect to x, the derivative of y is dy dx. Next one, y squared, take the derivative there, 2y, but since this isn't x and we're taking the derivative with respect to x, you'll have a dy dx tacked on because of the chain rule. Third one, take the derivative of 5y, you get a 5, but because y isn't x, you have dy dx. Chain rule again. And the next one, you're taking the derivative of x squared or negative x squared, depending on how you look at it. There's your 2x. And if you're thinking so strongly about the chain rule that you actually write down dx dx, that's no problem because dx over dx is another way of writing 1, so you just end up with 2x. On the right hand side, there's your 0. Next, once you've got all those, notice back here you had some terms that had dy dx and some terms that didn't. So you move all the terms that have dy dx in them to the left hand side, everything else to the right hand side. Next, you're going to factor out that dy dx like this. Now if you think of this expression right here as the same thing as, what if that were at 17? What would you do to get dy dx? You'd divide both sides by 17, or whatever the number was. Well, all we have to do is divide both sides by this, and the left-hand side will be just dy dx. So divide this side by the 3y squared plus 2y minus 5, and also divide it over here. What do we get? We've got dy dx. How about that? There's our 2x on the top, which was on the right-hand side, and what we divided by, the 3y squared plus 2y minus 5. Bingo, you got it. Here's a graph of that relation. It's not a function, it's a relation. Notice that 1, negative 3 is one of the points on that particular curve. So the derivative tells you the slope of the tangent line at any point on the graph. So you pick a point on the graph, any point, that point number 1 is going to have to fit in the x value and the y value in the original equation. If it does, then using this derivative or this slope, you can find the slope of the tangent line at that particular point on the graph. All you need to do is take that point, which is 1, negative 3 in this case, put the 1 in where the x's are, x in this case, put the negative 3 in where the y's are, and then do the calculations. Your slope is 1/8. Done. Find the slope of the graph of this one at the point 1, 1. So of course, to get the slope, you're going to take the derivative of this equation with respect to x. You're going to find dy dx. So you first write down the equation, make sure you got it correct, and you differentiate. Now you're differentiating with respect to x, so you get the 2x squared, bring that 2 out front, you got the 4x, and since it's x and you're differentiating with respect to x, you would have dx dx over here, which is a 1, So all you have is 4x for this first term. For the second one, bring that 2 out front, you get 2y, and because y isn't x, the derivative of y with respect to x is dy dx. What are we going to do next? We're going to get the dy dx term, this one, on the left-hand side all by itself. Subtracting the 4x, there's our equation, minus 2y dy dx equals minus 4x. Divide by negative 2y. There is our slope, dy dx. And that's our slope at any point on that original graph. Looks like I have an extra 1. I'll go back to 36 when I get finished here. 36, okay. Too many 1s up there, sorry. Now what this means is, at any point on that graph, if you find the ordered pair of some point on that graph, put the x value in here, the y value in here, and you'll have the slope of the tangent line at that point for that graph. Just put the 1 in for the x, the 1 in for the y. Notice I'll put the derivative up here with alias the slope. Put the x value in, so this 1 goes in here, this 1 goes in here, and there's our slope. And our slope is 2 for the tangent line at the point 1, 1 on that graph. Here's the graph for that equation. It's a hyperbola. Here's one of those points on that graph, and the tangent at that particular point to that graph has a slope of 2. If we want to find out what the equation is for that tangent line, all we'd have to do would be to use the point slope form. You remember what that is. Y minus y sub 1 equals slope m times x minus x sub 1. X sub 1 and y sub 1 are right there. There's a slope m. Clean it up and you've got your equation as well. And of course, applications are very important for business calculus or calculus for the social sciences. So we'll take an example here. We've got the demand function. Remember, the demand is an equation that has the price, the unit price for the item. So if we're selling, I guess if we look down here, maybe what we're selling is pairs of needle nose pliers, whatever. This P represents the price for one of those needle nose pliers. And for that particular price, X represents the demand or how many we can sell of those needle nose pliers. Here's our formula that puts those two together. What likely is the case is this just didn't come out of the air. Someone did some research and developed this equation, this model for how the price and the demand are related. The question is, find the rate of change of the demand X with respect to the price P when X equals 100. In other words, how is the demand changing compared to the price when you're selling currently 100 of those needle nose pliers per day or per month or whatever it is? So we'll start off by rewriting the function. First of all, there's our function. The first thing we're going to do is a bit of algebraic juggling around. In case you're the slightest bit confused, this part that's in the denominator, we multiply both sides by that, so you end up with just a 3 on this side, and this on the left hand side with the p, but at the same time you're going to divide by p, so this p ends up over here and is canceled out on the left hand side. Now, once you've got that down and it's in a form you can use, take the derivative of that. Remember, you're going to rewrite this as 3 times p to the negative 1, most likely, instead of using the quotient rule. Excuse me. And you're going to use implicit differentiation to get the derivative across this equation. You get the dx dp terms on the left side. Then we'll factor the dx dp out, and we'll divide those sides by the coefficient that you see right here. That way we end up with just dx dp, which is that one. There's our derivative. So, what we were interested in, when x equals 100, in other words, when we're able to sell 100 of those needle nose pliers, the price P can be figured out this way. This is from the original equation. Put the 100 in because we're able to sell 100 of those pliers. There are 2 places where the x shows up. Just do the arithmetic. It comes out to $1 for one of those pairs of pliers. It must not be very expensive pliers. Now, what we're interested in is when x equals 100. At that point, we're selling 100 if the price is $1 per pair of pliers. We just found the derivative, or the rate of change, dx dp, number of items per $1. How many of these can you sell per change of $1 per pair of pliers? Just put the 1 in for the price in our derivative, 100 in for the x values. There's our expression right there for dx dp. Just do the calculations, negative 75. So what does that mean? That means when we're able to sell 100 of those needle nose pliers, the demand is dropping because that's negative. It's dropping at the rate of 75,000 units for every dollar increase in price. So increasing the price by $1 means you're going to sell 75,000 less of those needle nose pliers. Quite a bit. And that's it for implicit differentiation. Now it's up to you to attack some of those questions in the book and see how you can do. And then bring those questions to our next Zoom session, and we'll see if we can keep you on track. And that's all for now. See you later for the next lesson, which is on related rates, where we'll use some of this implicit differentiation in a way that you might not expect. See you later. Bye-bye.